I hope you all got caffeine enough to enough to more get food for the brain. This is all food for the brain, okay? So, uh, well, let me start with a generic statement. In physics, the what are the most precious things? Symmetries. We always crave for symmetries, find symmetries and break them. Do not uh, forget this because we will come back to this again and again until we finish this lecture. So, and also another one remark is, I mean, in my opinion, the greatest physicists always develop both theory and also aware of what is happening in the observations, and always like observations and theory has to go hand in hand for us to progress. And in this sense, Starobinsky, who unfortunately passed away last year, it's a huge loss for the theoretical cosmology and observational cosmology, but he has pushed the boundaries of knowledge, and he has influenced generations with just few papers in the early stages of his career, which is a lesson for us to really how we want to do physics. And that is, we have to really remember that Stravinsky's first paper, one of the 1985 paper with Kaufman, his student, is about uh, CMB, lambda CDM, even before dark energy I mentioned yesterday. That is another, like how to write a toy models which help us understanding universe. Lambda CDM is a toy model. There is no theoretical foundation to it, but it's a clever model that tells us, you need to understand it in much more deeper level. Let's say, for example, let's compare it to, thermodynamical laws of physics. From where the thermodynamic comes, microscopically, this statistical mechanics, quantum statistics, thermodynamics is an emergent phenomena of some microscopic physics. And in the same way, lambda CDM somehow may be emergent from a very fundamental physics, maybe some approach of quantum gravity or combination of approaches of quantum gravity. What you heard in this in all these lectures that people gave, all different thoughts, every thought is precious. And we need to collect those precious thoughts and re-examine from questions, foundational questions. Sorry for the speech, I will go back to math. Okay, so what did we learn? We learned about power spectrum from the Starobinsky theory. Let me call it as a theory because this establishes a foundation for the start of the universe and gives several thoughts about the beginning of the universe. Okay, well, model gives prediction. That's great, but also it establishes a paradigm which has pushing many of us. But let's try to understand a different phase of the same theory. You see, what Einstein told us, geometry is matter. And you say, what we are saying is, okay, well, you modify geometry, geometrical modification of gravity. So you add R square term, gravity takes care of formation of universe. Just gives you as a freelance R square term. But you can also try to understand it. Oh, how R square term, if you think of it as some matter, but still even if you write some kind of matter, it is still a gravitational degree of freedom because it is coupled to gravity. It is determining the dynamics of the universe. It is determining the whole metric fluctuations, which are the seeds for large scale structure of the universe. Okay, we should not forget that. But without forgetting that, we can go to a frame called the Einstein frame, which is popularly well known as a Starobinsky model, at least in Wikipedia, ChatGPT, it gives you Einstein frame. So ChatGPT is not educated, okay? If it is educated, it should give you this, it should give this one, this Lagrangian. So whoever runs ChatGPT, they do not know physics. Now, But still, let's try to understand this. R plus R square. One excellent trick in physics from all the way from classical field theory from is called Lagrangian multipliers. I hope, I am sure you all know about it. We use that Lagrangian multiplier to establish a different picture of the same Lagrangian. And let's pull this half factor out and write mp square plus 2f0 r. I already made mistake. That is the Lagrangian, you cannot make mistakes, but here you can. So, but anyway, so you can write it in a different way like this. I hope it's correct, but we can check this. Okay. If you vary this Lagrangian with respect to phi, what do you get? 2f0 r equal to 2f0 r. No, something is wrong. Well, 2f0 r, you put a half factor here, then equal to f0 phi gives you phi equal to r, and you substitute it back there, you will get the original Lagrangian. It's just a Lagrangian multiplier. You don't need. Okay, let me look at my note. Two factors are the enemies for physics people. Without the factor of two? Yeah. Yeah. Yeah, because there is two factor cancel. Yes. Sorry. Yeah, there's two also there, and this gives you five equal to R. Thanks. If you're close to the board, you actually sometimes go blind, at least. People like me. Okay. When you write this, you get back the same Lagrangian. Cool. Then you see that, what is the scalar field? Well, scalar field is Ricci scalar. Remember that Ricci scalar, Starobinsky model makes the Ricci scalar dynamical. The trace equation of Starobinsky model is box square r equal to m, box r equal to m square r. The universe is formed by eigenstate of Ricci scalar by box operator. This box r equal to m square r gives completely inflation, exit from inflation, matter dominated era, and all the particle production kicks in. Everything we know, we want, can be produced from here. Of course, unknown elements of lambda and CDM. Let's put that. So this is the equation. It is eigenvalue equation because this is a R Ricci scalar is eigenstate of box operator. Okay. Now this is exactly that dynamical field phi. Now you do a something called conformal transformation. The transformation is basically you write v mu nu. Well, let's say you have this Lagrangian, the metric is g mu nu, and you define a new metric, which is some omega square, which is function of phi g mu nu. You kind of understand that what I'm doing here, because there is a factor here. The idea is to absorb this factor into g mu nu. And of course, this absorption also leads to change of Ricci scalar, because Ricci scalar ultimately depends on the derivatives of metric, etc. So, and see what we get. To do that, we will start with the generic Lagrangian to understand everything. And I'm starting this generic Lagrangian just to make it useful for you to extend this technique even for the complicated Lagrangians. And I hope it's in my notes. Yes. Okay. If you look at this, a field non-minimally coupled to Ricci scalar, right? But it has no kinetic term and just some potential. Okay. Let's start with the Lagrangian. 1 over 2. Uh, ah, yeah. Integral d4x square root of minus g. I'm starting a different Lagrangian, okay? Just to see how this Lagrangian gets transformed into a frame called Einstein frame. So to understand this, I'm writing a generic Lagrangian of this type. I wrote something p of x phi. You may be wondering what the hell is this? Okay, I'll explain. Wait. So p of x phi is function of x and phi, and it is expanded in terms of minus phi plus some k1 of phi x k2 of phi x square, etc. What is x? X is the usual kinetic term d mu phi d nu phi. Well, to be explicitly, this is a minimal coupling. Okay. And you can see that if you plug in it here, if I put k1 equal to 1, it's just some Lagrangian with a scalar field and some potential. But there are these x square, that means some higher order terms in general you can expand, and this is basically in the view of so-called EFT. Anna has presented that in the first 2 days, the EFT of scalar fields. So uh, we just write it for generic expansion, and we don't use it, but it's good to keep derivation general. Now we write this g mu nu as some omega square phi, some function of phi, and well, let me call it as g mu nu tilde, the new metric omega square phi g mu nu. New metric is some function of phi times the old metric. Once you do that, what are we doing by this? By doing this, okay, we need to understand it. Let's say we try to understand it in the context of FLRW flat spacetime. What is FLRW flat spacetime? This is dt square a square x square. G mu nu is the metric that is -1 a square a square a square, all the off diagonal terms 0. This is a metric, and we write this new metric g tilde mu nu, and we multiply it with omega square phi of the old metric. And we can absorb this omega square. If you look at this one, a square, okay, you can redefine your scale factor as some omega of phi, scale factor tilde, omega of phi, the old scale factor. Just following this rule, because you have scale factor square, you redefine it. But in the 0, 0, 0 component, you don't have anything. You just have time. So you redefine time there. The new metric time interval is some omega square phi, some d tilde. Sorry, dt. Okay, so you would redefine time. That means the concept of time in this new metric tilde is not the same as the old metric. But if you do it in conformal time, which is a square of tau minus d tau square dx square, and if you write it in conformal time, in the conformal time it is fine because you have the scale factor, so you can keep this definition in the conformal time. In both the frames, the conformal time is the same, which means that, okay, this is actually means that when you quantize fields and you do it in conformal time, you do not change the time thing in the for the quantum field. It's just a minor observation you can make. But anyway, once you do this, well, if you do the calculation, the Ricci scalar of old metric, because new metric I put with tilde, okay? But let me change a notation so that I do not do mistakes a bit. Let me write this. So when you compute the Ricci scalar of the old metric G, okay, it is related to the Ricci scalar and some bunch of terms that depends on the omega. And I instead this new metric Ricci scalar, I'm calling it as RE. It just represents Einstein frame. I will define what exactly it is in case if you are confused about it. But if you know, you understand what I'm doing. What? RE is R tilde. Yeah. And box E is a D'Alembert operator and in its tilde. I wrote it in my notes in this way, so just to keep the track, but maybe it's better in the final notes. I will correct the notations. Okay. Now, if you do this, you can make an observation here. Your old Ricci scalar in this new in this formalism is old Ricci scalar is equal to Ricci scalar of Einstein frame plus some dynamical thing associated with the conformal transformation. So your field dependent conformal transformation just gets the kinetic terms by construction. So just by a matter of computation. Okay. Yeah. Uh no. Well, minimal coupling will also be there. Non-minimal coupling will not be there. So basically, the non-minimal coupling is whatever if the phi field is coupled to directly to Ricci scalar. If it multiplies like this, it's called non-minimal coupling. Okay. And well, I don't know why. Well, it's just non-minimal coupling, and maybe I will skip some of the explanations of this. But anyway, yeah, if you do this and make a substitution everywhere, and you get an action. Oh, well, let me. So we start with this action, right? Let me call this action SP. P means just the use the notation P. Okay. So this action will turn out to be dt d cube x minus square root of minus g omega power minus 2 f of phi and re minus 6 d mu ln omega d mu ln omega plus p tilde, because this is function of phi and x, and now the x gets transformed, so that means it is function of phi and x tilde, and x tilde is with respect to the new metric. You just invert this relation, so to write it in terms of to write what is x tilde. The point is, yeah, well, is with respect to the tilde, so new G tilde mu nu. I just didn't write it there. It is I wrote it there. So it says in that expression. I hope you can see. Oh, yes. Okay. So, yeah. Once you write this, I'm just going a bit slow here, just for you to understand everything. Well, there is another term, 6 box ln omega, and now I define omega to be f of phi. Okay. Now I choose omega to be f of phi. That will remove this non-minimal coupling, and we are left with just the Einstein-Hilbert term. Then all the rest, some kinetic term related to omega, and you get the new Lagrangian with Einstein term and a minimally coupled scalar field. Is that concept clear? So if it's clear, then I will just skip the steps and apply this procedure to Starobinsky model. Right? No, omega is equal to f. Because if it is omega is equal to f, by the way, it is now it is written in terms of tilde because omega is equal to f, and I can get rid of this. Sorry, I'm blind. Okay, thanks for the correction. So if you do this procedure and then you get a Lagrangian for the Starobinsky theory, uh, square. Well, here omega square in this transformation is omega of phi is square root of this term mp square plus 6 f0 phi. No, 2f0 phi. Okay, is it clear? So you see there is a phi square term, and phi square term gets the factor in the denominator is just because you write square root of minus g in the numeric g tilde. I should put zeta. I did put z tilde. So then in the numeric, and you get a factor. That factor basically exactly divides. This is omega power 4 factor, and you can compute it. And the detailed computation will be in the notes. But still, it's not in. It's not fully in the familiar form. Well, the point is the following: you get the Einstein-Hilbert term, you get a scalar field with a kinetic term, but multiplied by some function exactly in like something similar to here. And there is some other, this is the potential term. Then you do a field redefinition. By the way, none of you asked the question that I do this transformation. Is it fine to do the transformation? Or is it always fine to do the transformation? No. This function has to be smoothly behaved everywhere in the manifold. Otherwise, this function, this transformation is not invertible. You need the transformation to be invertible. It's a very important condition. And at least during, for the context of inflationary, around inflationary space-time or anything, we make sure that this always remains positive and this never crosses zero. And Ricci scalar, which is phi is Ricci scalar, right? This is just Lagrangian multiplier, it is Ricci scalar. Phi is positive during inflation. That's fine. And at the end, GR term dominate, MP square terms dominate, this becomes subdominant, and you end up with the regular physics. So this is fine. But this is only in the context of inflation. Suppose you start with an FLRW spacetime with closed curvature. I mean, the spatial curvature. Let me write it here. I already received a complaint that I should erase the things and write. But the problem is I do not want to erase that. Okay, this can be erased. What did you want to explain? Yeah. Okay. So, so Ricci scalar for the generic FLRW is 12h square plus 6h dot plus 6k by a square. This is k denotes the spatial curvature. Imagine, because inflation, this term is dominant, this is not there, this is always small. even at the end of inflation, you keep that Ricci scalar positive. But when you include this term and try to understand what are the solutions of this Starobinsky theory, generic in FLRW spacetimes, you can have a situation where H dot is negative because K, let's say K equal to 1. Spatial curvature is positive. Okay. Then this is positive, but there is one term that can be negative. What does it mean by, well, when H dot is negative, you get the decreasing H value, right? Yeah. And if it is huge, if it dominates this term, you are in trouble because the Ricci scalar can be negative. If the Ricci scalar can be negative, this conformal factor may cross zero at some point. It may vanish. And then your conformal transformation is not valid. And indeed, in the recent paper by Muller and Stoporinsky, they find a bouncing solution which only exists in the Jordan frame, the original frame. So do not get mistaken that conformal transformation, you can always do it, that you hear this all the time, but it's important to pay attention to math. Math is language. We should not play with language. Mathematics is a very precise language. Otherwise, you get killed. Remember that story I told you. The kid comes and say big cat and the father get killed. So we miss something very important. We should note always the conditions under which we can do transformation and go to a frame. So as Starobinsky calls it, he said once in a conversation that this frame is a physical frame and this frame is a calculational frame. We will see what does it mean, because normally if you are used to something, you feel that that is simple. If you are not used to, you feel that that is complicated. You see the movie Alice in Wonderland. He lives in a normal world. Everything looks trivial, even the small things. Okay, just small things. But then he goes to the Wonderland from the normal world and he sees, oh my God, even the table is scary. Okay. Yeah, Einstein frame is what people are used to. It looks normal, and the Jordan frame looks scary. But that's why we started with other way around. That's the Wonderland. And we go to the normal land. That's everyone used to. If we know both, we do well in physics, hopefully. Okay, cool. Once you do the redefinition of the field phi tilde, well, you see, I use the phi here and phi tilde, but it's the same phi tilde. Yeah, it's a conformal transformation. So let me put tilde here, okay? Sorry for my notation. Just okay, I put tilde here, but do not get confused. So I do a field redefinition and go to a well-known thing, G tilde is the Einstein frame, and do not get confused. It will be clear in the notes. The important point for us for now to remember, we go to the Einstein frame. We go from Starobinsky to Einstein frame. This is, let me call with a phi for phi. And it comes with a specific coefficient. For this specific coefficient, I think I want to resurrect the term MP square so that you can clearly see everything dimensional fully and try to understand. Okay, we got, thanks, perfect. We got to the Einstein frame where there is a scalar field, which is a manifestation of the extra degree of freedom, which you do not see, but actually now you should see, right? You have got a better eye math. So all the time we spend on this. So now it should be clear. Anyway, we got this frame and this is what people are used to, but you have to make some very important notices. On this point, well, I should thank Anna for mentioning this during the coffee break. R square coefficient, F0, is mp square by 6m square, and you have a scalar degree of freedom whose mass is much less than Planck mass, because this is a theory which is describing some evolution of universe at very low curvature scales than the Planck scale, and you demand that whatever the extra degree of freedom is driving, the mass has to be much less than the Planck mass, and this is the physical condition you make. And in this frame, well, you see that under this condition, F0 is very large. But it is still very physics way below the Planck scale. Remember this. Do not forget. This is the most important message. Yeah. F0 is dimensionless. Okay. So let me write this way. And now you see the propagator and see what is the degree of freedom, how the new degree of freedom coming from R square, which we saw actually in our derivation of cosmological perturbations. Okay, and that's the mass of the extra propagating degree of freedom, and it is mentioned in the Lucas derivation of the propagator. You get an additional pole which describes the mass of the new degree of freedom, which we will see naively in the other approach. Is that clear? Okay, fine. You can do the mp square, m square, or mp square, but how do you read the mass? Mass is, if you write the propagator has to be 1 over k square plus m square, right? And if you do it other way around, yeah. Any question? Here also dimensionless. Yeah. 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 So it's just yeah. I think it is. I put Planck mass 1 equal to 1 or not equal to 1. In principle, you should put mp square or some convention. It is, in this case, phi tilde is dimensionless. So which if you take that, no, it's not. Yeah. No, wait. You want to have four dimensions, right? Phi tilde is Ricci scalar. Ricci scalar square. It has dimension 4. F0 is dimensionless. And then mp square r, 4 dimension. So it's fine. Yeah. But let's see, substitute phi here, and what is the dimension? It is r square. Does not have the same dimension of the F naught is dimensionless. Phi is same dimension as r. Yeah. Is like it just doesn't work in the last line. Yeah, I put m Planck equal to 1 here, so there is no m Planck here. Yeah, sorry, I'll just switching on and off m Planck, but okay. I will make this precise in the notes. Thanks for finding out. Okay. Look, so the coefficient of r square is large, but you do not get confused. It is large. It doesn't mean Planck scale physics. It doesn't mean it is this is describing some quantum gravity regime. It is describing only low energy regime, as same as this theory describes, because this is just a conformal transformation. People normally give a argument that Starobinsky model has a problem, that whole coefficient is huge, because if people they give that argument, they don't know what is conformal transformation, and they do not know what is that frame, Jordan frame, and they do not care to understand what means of Jordan frame. That is a physical frame. This is a calculational frame. Okay, I hope that point is clear. Once this is clear, there is another point. Look, we are introducing anyway a new degree of freedom, new scalar degree of freedom. It is needed if you want to explain data. Theory don't like that term because from the perspective of EFT of GR, that one would be a strong coupling That's not a strong coupling regime. Yeah.
Start from a different with different degrees of freedom.
Yeah. Yeah.
So in sense here. Yeah, that's right.
But this is not EFT of GR. This is a new degree of freedom. You need it to explain temperature fluctuations in the CMB. Even if you include, like, okay, you do not like inflation, you want some other mechanism, but still you need a new degree of freedom of gravity. It can be anything, but you need a new degree of freedom. If you say, if you are close to the EFT of GR, you are not adding a new degree of freedom. That means you do not care about CMB.
Yeah, be more precisely, when EFT of GR holds here is for energy smaller than M.
Yeah.
So
yeah.
in sense, what you're saying, the EFT of GR breaks down the one at this scale M that would be the lambda you have your that's yeah, which is actually very nice consistent with the Gucci bounded you mentioned. Yes. Which is the scale. Because it creates another potential problem, which is that in order to be able to truncate the thing there reliably, all the higher order terms cannot be suppressed by the same sure. Which means that through you get out anywhere else, and there's some huge gap. That's fine. But if you add the bicycle there, you would have something normalized in the case. Sure, but that's something.
Just to interrupt. Okay. Yeah, I just want to. I don't want to lose time, and Benjamin will say, "I don't care about that." So okay. I hope that point is clear. You need a new degree of freedom that is a non-perturbative modification of GR. Just to put it this way, okay? And it is needed anyway if you want to explain CMB. So okay, if you plot this potential, it kind of look like this. You see, when scalar field has large values, the potential is flat. That means basically your dynamics of the kinetic term are slow. That's called slow roll, and which is what all the popular lecture notes of on inflation describe. But unfortunately, the popular lecture notes do not start with inflation, which is the first theory of inflation came from Starobinsky. They start with saying that, okay, well, you see the CMB, you have the horizon problem, flatness problem. Yes, there are problems, but the lecture notes do not start with symmetries. Symmetries are physics. De Sitter is a symmetry, and you break the symmetry and you get universe. Symmetries are the precious things in physics. We need to take care of because that's not, we have not failed in physics as far as we see the symmetries. Look at the history wherever you touch. And even actually, you are in the string theory lectures by Ivanov, he was mentioning about conformal symmetry. It's also a very important symmetry, which is related to the conformal transformation. Okay, and there is a symmetry that R square Lagrangian holds. When universe is dominated by R square, the R square term is scale invariant. If you look at R square and you do a conformal transformation when omega is constant, this R square term, this constant disappears. There is a scaling symmetry R square term has. But this symmetry is destroyed by Einstein. Because of the Einstein term, this scale invariance is broken. And because this Einstein term is subdominant during inflation, this scale invariance symmetry is slightly broken. That's what gives the power spectrum we have derived a while ago. So that scale invariance can also be seen in the flatness of the potential here. And there are a lot of literature says that, okay, flatness of the potential is not natural from the quantum gravity point of views, and some particular quantum gravity frameworks. No, natural is a question of is subjective. What is natural is to understand symmetries. So exactly, the scale invariance is the symmetry, and that is natural. Universe exists because of accidents. The accidents are breaking of symmetries. I'm saying this word, I learned this from a lecture which is available in somewhere in the internet from Murray Gell-Mann. I'm just repeating his words. Very important words. Universe exists by accidents, and it's all symmetries are broken. And everywhere you see, if you go to high energy scales, you do not change the basic structure of physics. It's like the layers of the onion. You go to the smaller and smaller scales, you keep seeing the same thing repeating. And we saw it. I mean, if you in the previous discussion, we were discussing about harmonic oscillators, inverse harmonic oscillators, quantum fields, everything about very high energy scale. At what energy scale we are talking about? The curvature scale during inflation is already of the order of 10 power minus 4 Planck mass. That is 10 power of 14 GeV, which is way above the scales we experience in the, for example, in the large hadron collider. But still, it's the same physics, it's the same thing, just manifested in a different way. So we have to see that universal nature of it, and that is very important. And once we have this one, so all the rest is very easy derivation. And you can, I'm skipping also the inflationary perturbations in this because there are a lot of reviews exist, but let me give you intuitive picture. Ricci scalar perturbation, that is the Einstein term, you have two Bardeen potential, phi and psi. And you have the scalar field perturbation, delta phi. You have three, but out of three, there is only one quantity which propagates. And this is the quantity called the curvature perturbation in the co-moving curvature perturbation, which is related to psi times delta phi by phi dot times h. It's very similar to curvature perturbation you saw in the Jordan frame, that is the Starobinsky's geometric frame. Okay. There is also another condition from the perturbations which you arrive at phi equal to psi. But these are Bardeen potentials of Einstein frame, and they are equal. But in the during inflation in the Jordan frame, these Bardeen potential phi plus psi are approximately zero, phi equal to minus psi. But at the end of inflation, you get GR domination, phi becomes psi, because there the metric degree of freedom is as that extra propagating behavior that is scalar on. Here you see it, you kind of separate it in terms of this new field, but at the end of the day, the propagating degree of freedom is a combination of metric and matter, if you want to see, because this gives you energy momentum tensor. If you ask the question, what is creating the CMB temperature fluctuations? It is gravity. Okay, people use the gauge choices, but even whatever the gauge choice you use, you are writing an effective degree of freedom that will give metric fluctuations, and that metric fluctuations is exactly what you see in the CMB. Do not get confused. Literature sometimes really confuse you and put you in a conundrums, but there are important references I will definitely give in the lecture notes where this is very precisely described. Point number two. Whenever we take this effective degree of freedom, we quantize it. Quantizing means we elevate the degree of freedom to an operator. But we start with the classical spacetime, which is whatever the inflationary spacetime, which is quasi-de Sitter, but you put quantum fluctuations on the top of it, but then also consider the back reactions, everything, okay? What does this all mean? It is linearized quantum gravity at the linearized fluctuation level. So just remember that the definition of quantum gravity is not something only comes at the Planck scale. The definition of quantum gravity can occur at any scales, and especially when you have particle horizons or event horizon, whatever the horizons, and especially in the context of inflation, you have a horizon exit of inflationary fluctuations, and at the linearized level, you see metric fluctuations behaving quantum mechanically and giving you precise prediction that is exactly near scale invariance, which you see in the CMB. Okay. Then you ask a question, okay, what about non-linear fluctuations? You can go to the next order in perturbation theory. That means how this new degree of freedom, which is gravitational degree of freedom, which is self-interacting, right? It has self-interactions and also it has interactions with the graviton at the nonlinear level. Because when you perturb the metric in terms of Bardeen potentials and Hij tensor, and at the at the nonlinear level, you because when I say nonlinear level, look, when we derive all these things, we derive second order action. But equations of motion are the linearized equations, right? Nonlinear means you go to the third order action. That means you are taking into account interactions, and these interactions will give you so-called non-Gaussianities, which are basically associated with the 3-point correlations in the CMB. So power spectrum is 2-point correlation, and non-Gaussianities are 3-point correlation. So I will skip that. I plan to explain that better, but I hope intuitively you got the picture, and there's a lot of literature available. And if you specifically want to see how the non-Gaussianities look like in the R plus R square Jordan frame, and which is, to my knowledge, the first time derived in our paper with Alexei Koshylev and Alexei Starobinsky, it was in a non-local gravity setup, but at least you can see the result of R plus R square non-Gaussianity in the Jordan frame. So message is, do not get scared about Jordan frame if you ever have to deal with it, because it is completely understandable. So I hope you are familiar with the normal world and wonderland. Okay, now let me check what the rest I want to present, how much time I have. Okay, maybe let's take 2 minutes break. Yeah. Uh, shall we continue? Okay. Okay. Let's continue. And I'm from this part onwards, I'm deriving less. I will speak more. Sorry if it is boring, but please feel free to ask any questions. Then I will derive. So, because I have some list of 20 topics, but these 20 topics are not for the rest of the time. Just I covered already many of them. I will try to. Yeah, I will try that. But uh, let me think in what are the. So I covered Anna, Ivan, who I covered, and Benjamin and Alessia. Okay, I will think about it. So there should be some connection to make. Okay, before going that, let's try to understand. You see, as I explained, you have CMB angular power spectrum. CMB angular power spectrum is given by the integral 2 by 9 pi. The power spectrum derived the initial fluctuations. We derive it in the context of inflation, but you can derive it in the context of any cosmology you can do. Yeah. Okay. Well, this is just a special functions, but that gives you the angular correlation. I will erase it. Yes, I cannot see your face. Look, oh my God. Okay. So, but as I already told you, the power spectrum expectation that how the power spectrum look like is already guessed by the Harrison and Zeldovich. Interestingly, Zeldovich in 1974, he expects that how the power spectrum look like, and he also thanks Alexei Starobinsky, who was his student at the time. What a great teacher who thank very honestly the student for the contributions. That's a great relationship, I believe. I don't know what's the relationship between them, how it went, but just I'm speculating. Okay, look, this power spectrum, this is some amplitude k by k star whole power ns minus 1. And we derive it from inflation. And how did we derive it? We wrote the Mukhono-Sasaki variable, we quantized the Mukhono-Sasaki variable, and how the Mukhono-Sasaki variable during de Sitter is something, de Sitter approximation. You can always find some slow roll corrections. But at least the leading order, it gives you something. So you have Mukhono-Sasaki variable like this. Okay? You have here 2 by tau square. Let us, you know that I did some exercise before. You take a scalar field in a de Sitter background. Okay, and we derived that how we rescale the scalar field with phi tilde with the scale factor, and we obtained similarly how this how this the same equation of phi tilde looks the same as the equation of Mukhono-Sasaki variable in the leading order de Sitter approximation. But let us do another piece of exercise. It is that I do not want de Sitter, and I want to understand how to quantize field in a generic FLRW background. Let's keep the flat FLRW background just for simplicity. Trick is always the same. All we know as human beings, harmonic oscillators, nothing else. So, what is square root of minus g for a generic action is a power 4, because for a generic, right? You write any generic FLRW metric, a square times conformal to Minkowski, because we always try to find a structure as close to Minkowski, to understand really what's going on. That's our guiding principle. Okay, well, we write in this frame, and you can still do the same kind of redefinition, but now it is not de Sitter. Okay, the scale factor is arbitrary. Now let me write the box operator 1 over a square in the conformal time di tau square minus 2h. This is just Hubble parameter in conformal time, and plus di square phi. And there is 1 over a square, you cancel it. We did the same exercise, but now this time the scale factor is not exponential of ht. It's different. Let's try to proceed generic derivation, and then we see what we get. If now rescale phi tilde as check it out. I'm checking. So you rescale this field, and then you get an action which is d tau d cube x times phi tilde minus d tau square plus di square plus a double prime by a phi tilde. Okay, you can derive it. It's very easy.
Just add a mass term to this without using it.
Yeah, well, you start with a scalar field which is massless. Yeah, of course. Yeah, of course. Yeah, it will not change anything, but there will be some factors of a floating around the mass divided by a square or something. I don't remember exactly, but in principle, you can extend it for the massive fields. And indeed, understanding massive fields has some role in cosmology as well, so which I will try to mention. So thanks for the question. Yeah, and when you do this, now you look at a double prime by a in the context. In the case of de Sitter, let's erase this piece. I will write this Smukhanow-Saki equation again. Do not worry. So in the context of de Sitter, a is exponential of ht, and a in terms of conformal time is minus h1 by h tau, and you compute a double prime by a, you get minus 2 by tau square. It is some negative inverse harmonic oscillator. Do not forget. I will mention about this, why this inverse harmonic oscillator keep appearing. But in the case of de Sitter, it is like this, right? But let us try some scale factor. I will explain what the scale factor is. I would be happy if you guess the scale factor. My scale factor is a equal to tau square. Any guess? It's fine. We will go to what the scale factor is. But then compute a double prime by a. What do you get? Or the minus, right? Yeah. Should be a minus sign somewhere. Let me check this. Uh, yeah, it should be fine. Then it looks like a normal oscillator. Okay, but you can try to study the spectrum of these, but it has similar equation, but the mass term is different. Okay, but you see there is a difference between that one and this one. This one is related to scale factor in the cosmic time p power 2 by 3. It's a matter domination. Okay, it's a matter. The scale factor in GR you get, if you put matter, you get that scale factor. We discussed this in the first lecture. But With this scale factor, the Hubble parameter is 2 by 3t, right? It's not constant anymore. It has some time evolution, different from normal, but this doesn't give you accelerated expansion. It gives you contraction. The universe keep not, it does not expand accelerated way. So it kind of, this expansion keep reducing. So it's called contraction. And there are models try to get scale invariant power spectrum with a matter dominated contraction, and but still they cannot easily get it because you need some exit from that phase and try to see get if you get particle production or all the stuff. There are troubles. But in principle, you can get a scale invariant power spectrum just just due to the fact that you want to get some term. But in this case, it's the fluctuations do not exit the horizon, but they enter the horizon, but still they become constant. So the cosmic history is a bit different, but still it will give you something exactly scale invariant, but to get ns just close to 1 with exactly ns minus 1 to be minus 0.04 is a difficult thing. And to get that, the frameworks need models with the scalar field potentials. Let's say if you have action square root of minus g r by 2 d mu d phi square and some potential. You see, normally in physics, we always take the potentials to be positive. Okay, well, this potential, not that effective one when you get rescaling, but that's a trick you want to you use it to quantize the field, but that's not the thing. In the original action, you write a kinetic term and a potential, and normally you take the potential to be positive. Let's take Higgs potential. It is positive, Mexican hat, right? But to implement to get a power spectrum, scale invariant power spectrum in this kind of matter type contraction, people need negative potentials, the runaway potentials, and it needs requirement of some physics way beyond our usual 4 dimensions, or some framework of string theory gives that, and there are some explicit calculations. So the people propose the models based on those some calculations, but those calculations also have a lot of assumptions on the beginning of the universe, like brain collisions and extra dimensions. Sure, they are interesting for sure, because we still do not know what is the absolute zero of time. What we know here is just some evolution close to the starting from a distant space stage. So all these investigations in the framework of quantum gravity do try to address the issue of absolute zero of time. Yeah.
So basically, there is an attempt to repeat the same calculation in this mathematical case.
Yeah. Yeah.
Like how to find a vacuum state in this case, like
Same trick. Same. But there is another thing. So in the matter dominated, these are the bounce models. So you define some initial conditions in the pre-bounce. So the universe before the bounce has all the scales inside, which are basically correspond to all the, well, then there's a bounce. After the bounce, things enter, but the physics happened before the bounce, then that becomes fluctuations become frozen, and that can explain the scale invariant power spectrum. But you can find various explanations, but then it is not possible to conclude with any experiment. Experiment requires more predictions, and that, for example, the primordial gravitational waves, those predictions are not precisely derived. They are based on the hypothesis and some expectations. And these cover matter type bounces, ekpyrotic cosmology, and also something, if you do it, for example, A equal to T power P, this is called the power law. Also, sometimes it's also called the power law inflation, because this is just an expectation that if you have a matter dominated error, radiation dominated error, you get some T power something. You just write some arbitrary P, But then you try come up with the potential, and this always happen to be the negative potential. Then it requires more and robust physical justifications. So as Ivano mentioned, there is this bottom to down approach. There's bottom to top approach, top to bottom approach. So this one is based on understanding of the QFT thing. So there should be some term which is bottom to top approach. Then, of course, we need quantum gravity at Planck scales. So you try to construct based on set of principles. Then bottom to down approach. Both have problems. We need observations to guide us. That means we need to derive predictions. Then you say that, okay, CMB is already explained. What else there? What else is there? We'll get back to that. I have perfect. As I said, it's mostly the story, and now I want to share screen a bit.
Sorry. There are places are not still ruled out. That was that assume like a scale factor going like T to the P. That P or like they are all ruled out, and the only one it's like W minus one, which is the same kind of the simple expansion.
Let me tell you a story. So before Einstein, there was Newton theory, and it had a lot of challenges. Perihelion of Mercury. If you watch this movie, Einstein and Eddington scratch his head to a lot to explain this. What kind of theory can explain this? And of course, at that time, there are a lot of modifications of Newtonian gravity, which are, okay, what I add this term, I add that term, I add that term, I add that term. You can keep adding terms to the Newtonian gravity and try to fit it everywhere where you see, for example, solar system or galaxies, everywhere. You can try to keep doing that. You get successful. This is basically the phenomenology. But Einstein theory has no new parameters. It has C, G, which are the parameters known. You put whatever your stuff and you know the curvature of space-time, and it explains almost a lot of observations. So which approach is better? Of course, those attempts surely must have motivated Einstein to think of a missing principle. But if you do not search for principle, I explain the data with some modification. I do not care about principles. That's not a good situation for physics. Fortunately, there are less number of people like that when Einstein proposed the general theory of relativity. So that general theory of relativity saw the light. But even then, it was not accepted by many physicists. It was Planck who pushed Einstein's theory further, and it gained attention. And ultimately, of course, observation, thanks to that technology at that time, exists. So what I want to say, the answer to your question, principle. What strong principle we need to explain the universe? If we do not have that, if you can keep adding the terms, fine, explain, publish, fine. There are a lot of models, papers exist. That's why it's very difficult in these times to get the right literature, right paper, which hunt for principles. So physics about finding for principle. It's okay to do the toy model. I gave the example, Starobinsky and Kaufman, they put the toy model of lambda CDM. No explanation, but still it follows a principle of explaining observations. So theory people should have their own principles. Observations people should have their own principles. Then look at each other and correct themselves with each other all the time. So this is what is needed. So I hope that answers your question. Okay. Can I share screen? Sorry, if I'm telling the story, you can understand I'm just in an emotional stage. Exactly same as Luca. So, ah, ah. Okay, this is the question which was asked, and now I'm I come back to answer this question. Hopefully. So basically, in the next 15, 20 minutes, I will try to explain the unknown missing things which we still need to understand and the current attempts of explaining them. And also, I will try to give more recent activities which are still related to fundamental physics. I think that's where I can uh, connect somehow to Alessius and Benjamin. So then the mission will be over. We will go for lunch. So, okay. All scale invariant power spectrum we are talking about is 1 degree. This is, let's say, 2 did I share screen? Yeah, sorry. This is 2 degrees. And above 2 degrees, things are not in causal contact now. But these are the, this is the prediction. The green line is a prediction of the scale invariant power spectrum with lambda CDM. Everything fits fantastically well. Oh my God, this is all large scale structure, everything with the initial seeds. Amazing. But go here, go to less than 10 degrees. There is a lot of fuzziness going on. We don't know what it is. Nobody knew what it is. So, what this fuzziness? Kobe satellite, you look at that picture, look at these 3 pictures, Kobe, WMAP, Planck. Kobe saw the CMB correlations at greater than 7 degrees. Okay? WMAP start to probe more and more less than 7 degrees. Planck has reached absolute precision towards all the way from 2 degrees and below. That's what you see. That's what you see more data points here. This scale invariant power spectrum is about 2 degrees less than below. So, cool. That's what we explain. Then, what are these huge red, huge blue spots? These are large scale correlations at greater than 10 degrees, roughly greater than 7 degrees. And most of them are basically, okay, there is this something called cosmic variance. The point number 1, the standard inflationary scale invariant power spectrum is not giving closely with the data points. And then I will explain the error bars. Then you can say, there are huge error bars. But this is basically, cosmology is a different field of science, not like particle physics. In particle physics, you take particles and smash them, get the data. You take more particles and smash them, get the data. You repeat the experiment any number of times to increase the accuracy of what you are measuring. You use a lot of statistics, and you have more number of data points, and you get more and more accuracies. But in cosmology, you cannot do that because we are not the one creating universe. It has already created, and we are looking what is left over and trying to understand and infer from them. This gives us a huge challenge that if there is something which we really need to understand as theoreticians, that closely what data, how they are measuring, and what are the details. And nowadays, most of the time, most of the data analysis is done by a lot of physicists who are moved from particle physics to cosmology. They still have a theoretical background, but there are set of data people who are been doing all the decades the data. So there is a imbalance there. So that's why sometimes you see data saying, this is possible, that is possible, that is possible, that is possible, because the data analysis also requires some principles. And this is something much more harder than theoretical grounds. But still, principles are always symmetries. If you look at here, so this is angular correlations. These are basically angular scales, the CL, okay? So, but see, L takes even odd values, right? So what you see here, 90 degrees. So L equal to 180 by, sorry, theta is 180 by L, and L equal to 2 is exactly 90 degrees. Okay. So then you have L equal to 2, L equal to 3, L equal to 4, and you have some zigzag oscillations going on, which is something not well understood. And in a recent data analysis, which involves my recent work with my collaborator, but of course he's a more experimental guy, so we were trying to see hunting for symmetries actually together. So but he's more into more know the data more. Okay, let's see. You see WMAP 357, and there is this P plus by P minus. Basically, it's the ratio of even to odd power. And you look at, you see, if you are going L equal to 100, that is 1 degree. Okay, but if you go to more than 10 degrees, because L equal to 40 is already 7 or 9 degrees, and then you go all the way down and you see the data hugely deviated from theory. And this is the analysis which has been there in the data analysis for a long time. Then you look at this curve, you see the green line is the curve related to the standard inflation with lambda CDM, but then there is the curve which is going a bit differently. So that means it's going down, it's going negative. All of this indicates, so I'm presenting a data just to give you an understanding of what data is telling us for us to think more about the theories. And basically, this map's telling you at very large scales, you have hot and cold spots, but at exactly 180 degrees, these hot and cold spots have the shapes which are almost mirror images of each other. If they are mirror images, you get more power in the odd multipoles and less power in the even multipoles. This can be worked out easily, and the data exactly shows that. And there is a parameter called RPT. It is there in all the Planck data, but it's in the, because you see the CLs are the Fourier spectrum, so it's in the ALM. But this is all like even by, let's say, odd, but you do the summation. So then this is something 0.79. So if it is a normally standard inflationary thing, inflationary quantum fluctuation scale invariant, so that fits data very well at 1 degree or 2 degrees, but it is something missing, this asymmetry, which is about 20%. So this is unexplained. And recently we made an attempt to do that in a theory called direct sum inflation. And it look at these angular correlations at exactly 180 degrees. The data all telling this, and this direct sum inflation goes indicating that there is something, it fits the data much better than the standard inflationary power spectrum. But direct sum inflation is not a new inflationary model. It's just a different treatment of inflationary quantum fluctuations. So this is just an example to see that quantum field theory in curved spacetime is still an untestable thing. So we tested quantum field theory in Minkowski spacetime, which is developed with hand in hand with the experiment. Quantum field theory in curved spacetime is new physics, and it is something we have to explore. And we obtained it with a particular framework of quantum fluctuations, but it is what we give here is a formula that fits the data, and it is something open, because at large scales you have more power in the odd than less power in the even, and we give a precise formula that is related to the NS, the spectral index. So it is important to understand this formula in a more deeper level, and because it fits the data, and also this gives a scope for further explanations in the quantum gravity research. So this is one message. And well, I'm done with this. So then there is what else going on in the observational cosmology? The other directions are basically gravitational waves, and there are a lot of inflationary models predict the different spectrum for gravitational waves. By the way, there is one thing which I did not mention, like NS, the scalar spectral index, which is 1 minus 2 by n, and you have also tensor spectral index, which is minus 2 Okay, I think minus 3 by 2 n square in the Starobinsky model. So, and this is basically you have the tensor power spectrum. There is a tilt to the tensor power spectrum, and this is what it is. And there is a relation called the consistency relation, minus 8 epsilon minus 8 nt. And this is another probe that future observations are looking for. And there are a lot of models, EFT models try to modify this. And also there are a lot of quantum gravity frameworks modify this. And one of the quantum gravity framework which will be discussed in the rest of the workshop is something called non-local gravity, which we have worked on, and where we show the same Starobinsky inflation can be embedded in a in a gravity theory with a lot of non-localities. The similar kind of non-localities, exactly what Benjamin and others here discussed. Okay, so that means this how non-locality affects the observations is something derived with some certain assumptions, but these non-localities are the precisely has to be fixed, and this how to fix these non-localities, these higher derivative non-localities, which Alessia Benjamin mentioned, is a uh, I mean, the way to fix them is using some principle, and asymptotic safety is such principle, which is something it can give us to test if there is a non-locality needed for quantum gravity. And of course, the calculations Alessia and Benjamin presented, they may be Planck scale, but you see, everything has an effect. You start with small. If you change the foundations a bit, it will carry on forward. So this is how we build brick by brick the physics and see the outcomes. Okay, so, and there is another direction. I mean, is it just CMB and what else? Gravitational waves? That's it? Well, no, that's not the end of the story. Uh, there are, the question is, are there more polarizations? Because CMB is scalar fluctuations, and gravitational waves, tensor fluctuations. Can there be more degrees of freedom which may affect the CMB physics? What about vector fields? After all, we see the universe for the first with our eyes with electromagnetic radiation. So vector field is one of the fundamental field in all our even day-to-day experience. Why not vector fields play a role in cosmology? And this is an active area of investigation, and people are looking for extra polarizations. And one recent attempt is a so-called parity violating features in the CMB. Well, that is different from parity I explained here. This parity is related to the still scalar. Okay, I mean, then you can ask, how can a scalar be parity? You see, if you have a function, scalar function of x, it doesn't have to have same values at x and minus x. Okay, it is a function of position. Okay, this one is what I described is something telling about an asymmetry in the CMB 2-point correlations. But then there is another thing which is related to parity violation, and this comes from a new physics. It's called this is basically in QCD, which is also Leslie Benjamin mentioned. You mentioned, yeah. In QCD, there is at least you mentioned QCD, but in QCD, there is a new particle called axion. And axion is a, well, interesting particle. It's also assumed to be a dark matter candidate. And if the axion coupled to vector fields, it will create new polarizations. And also there is a lot of axion physics going on, and it gives some new phenomena called birefringence. This is being explored by Ichiro Komatsu and collaborators. And this is another new physics to look forward to. So QCD is done, quantum gravity is done. What else? Not everything is done. I'm just saying that there are open questions which are still to be explored. CDM. Cold dark matter is something totally unknown component, and people have been searching if there is a cold dark matter particle or not. It's very extremely the most disturbing problem in theoretical physics, even more than lambda. Most of the studies, okay, well, if you put the term lambda, okay, fine, at least you can explain the data, but it is this term CDM is something affecting our local physics. It's around us, it's in our galaxy. We do not, well, lambda is still far away. for us to explore. The CDM is in our galaxy, or the outskirts of the galaxies. There's a dark matter halo we still do not fully understand at all. And one of the very interesting proposal put forward by Hawking, Zeldovich, Bernard Carr, another name, Novikov, is the proposal of primordial black holes. Indeed, in the early universe cosmology, you can have a situation where your primordial fields can collapse and form primordial black holes, which are different kind from the stellar or astrophysical black holes. But the current status is still at the beginning stages because nobody knows how the formation exactly happened. This is an extremely open question. And this is an active area of research, primordial black holes, and the primordial black holes could be the dark matter candidates. And in astrophysics, there are dark matter is a problem, but there are also other problems related to, for example, there are some galaxies which have these guys called quasars. Quasars are basically the supermassive black holes which are emitting the high energy jets of the length of kiloparsec scales. Huge, very bright galaxies. Unfortunately, our galaxy black hole is sleepy. I mean, just it's not very entertaining for us. It's better. We may do better physics if we live in a galaxy where the black hole is more active and it will inspire us to do better. So if we are not doing better, it's because of the black hole. So anyways, just jokes apart, this is these high energy jets are the places to look for new physics because we do not understand this how energy jets get generated. We do not understand the fundamental physics that is being played. So this is another question, astrophysics question, but this is also related to cosmology because when we measure the cosmic expansions, looking at the galaxies far away, and these galaxies with quasars are the troublesome galaxies because you cannot calibrate your instrument so precisely because there is a lot of unknown physics going on. So finally, we will end. I was there. Yeah.
I can read it out.
Yeah.
Is there any time to talk about gravitational wave memory?
No. Sorry. First of all, I do not know the phenomena very well. My knowledge is super limited, and I'm afraid to say something wrong. So, but that's fine. It's totally fine to say something wrong. Then it gives opportunity to correct, but there is no time. Sorry. Finally, observations are important, and theory is important. It's always hand in hand. We get sometimes inspiration comes in both ways. So let me give an example. 1916, Schwarzschild proposed the black hole solution just 1 month or 3 months after Einstein came up with the theory. Einstein thought, at least the story I heard, that Einstein thought no one could solve the problem, could solve the equations exactly, but Schwarzschild is an astronomer who has connection with observations. Also extremely equipped with doing a complex mathematical calculations, and he came up with the solution. 1916, fast forward until 1963, no new solution has been found until Roy Kerr, who found the rotating black hole solution. And after all, now we know that all the black holes in the universe, majority of them, are the Kerr black holes. But how Kerr got motivated to find the solution is just soon after the discovery of quasars, which I learned in a recent article. Well, he talks about a lot of singularities. There are different opinions, and that's okay. But the interesting element is he proposed that soon after quasars are discovered. So observations do inspire theoretical people, and let's please look observations to build our fundamental theories and quantum gravity. It is important. This is all the rest of the workshop is about. Thank you very much.